All right, so taking a look at today's stuff, filling in the blanks, we're going to be looking at not only just correlation, but also something that's called a residual. Okay, so as we learned yesterday, the correlation tells us the strength of the line. Okay, is it a strong correlation or a weak correlation? But just because it's a strong correlation doesn't necessarily mean that a linear equation is the line of best fit. So how do we decide if it's a linear correlation or not? We make what is called a residual plot. So that's what I'm going to show you guys how to make today. So once you are done filling in those blanks, go ahead and pull up your table, and you're going to go to Edit, clear any data that's already in there, and enter the new data that you see in the slide or on your notes.
Wait, Miss Beasley.
Yeah.
Do you want the thing found in catalog from yesterday's information on?
Yeah, you can keep it on. You don't need to turn it off. Okay, so you're going to go to Stat, Edit, clear whatever is in your L1 and L2, and enter the new data.
Wait, is it okay if you miss those 0, 0?
No. Just add it at the end. Doesn't matter if it's out of order, but you have to have them together. Like this. 668, 68. 2. And then 74. Right. From here, I want you to run your regression analysis and pull up the line of best fit. So we press Stat, we go over to Calc, choose choice 4, enter. And how many do you see an R value of 0.94? Okay, so what does that 0.94 mean? From yesterday, what does the 0.94 mean? Go ahead, Elizabeth. Good, so we're going to write that down. R equals, come on, 0.94, which means it's a strong positive correlation. Yeah.
Something's up. I can't do it.
Okay.
It says like error. Technically.
We're in L1 and L3. Clear L3. Clear both. And our equation, if we round like it says to round everything to the nearest 10, we get y equals 6.0x plus 13.1. Who agrees with both of those? Is that what you guys have in your calculator? We're good? Yes? Okay, so remind me guys, the y-intercept is what in this equation? Go ahead, Luke. No?
Where the time is 0.
Just tell me, yes, where the time is 0, so what is the actual number? What? What's the y-intercept? Help them out. 13.1. So what this line of best fit is saying is when time is 0, speed is 13.1. Does that really make sense in this scenario? No. You haven't moved yet, right? There's no speed. But this is the model. Okay, so but that's what it would say in relationship to the scenario. What does the 6 tell us? Dan?
That it increases 6 feet per second every second.
Very good. It increases at a rate of 6 feet per second every second. Okay? Change in y over change in x. Perfect. All right, so now we're going to go through the process of creating the residual plot. And it looks pretty challenging, but it's really not. I will tell you guys it's shown up about 4 times on the Regents where kids have actually had to do this process. So it is highly likely that you could see it again. You want to make sure you got this down. All right. So to create the residual plot, what we do is we do our actual values minus our predicted values to calculate the residual. Write that down somewhere so you have it to see. So we have to calculate the predicted values. To calculate the predicted values, we take the equation that we created, the 6.0x plus 13.1, and we plug in our x values and find our predicted y values instead of our actual y values. These are our actual ones right now. We're going to find the predicted ones. So if I plug in 0, what's 0 times 6? Everybody? 0. 0 plus 13.1. 13.1, but it says we can round to the nearest integer, so we're just going to put 13. If I plug in 2, what's 2 times 6? 12 plus 13.1. 25.1, right? Rounded to the nearest integer, we get 25. Okay, what's 6 times 4? 24. Add 13. 37. Keep going. Find all of the predicted values. Find it to the nearest whole number. Okay, so what is the predicted value when I plug in 6? What is the predicted when I plug in 6? Go ahead, Kyle.
49.
Who agrees with 49? Okay, what's the predicted value when I plug in 8, Emily? Who agrees with 61? Okay, Madison, what's the predicted value when I plug in 10? 73. Who agrees with 73? Okay, and what's the predicted value when I plug in 12? Marcus?
85.
Who agrees with 85? Okay, so now, to find my residuals, to calculate my residuals, I'm going to do actual minus predicted. We're good?
Here's 81.
I did. What was it supposed to be?
85.
Oh, God. I have no idea where that 81 came from. We good? Thank you. Sometimes I just say things and then write things down differently. It's not a big deal. We all make mistakes.
I make a lot.
Riley's being late right now. Okay. 0 minus 13 is?
Negative 13.
Negative 13. 25 minus 25 is?
0.
0. 46 minus 37 is? 9. 60 minus 49 is?
11.
11. 60 minus 61 is? 72 minus 73.
Negative 1.
74 minus 85.
9.
Negative 11, not negative 11. Wait, no.
Negative.
Yeah, negative 11, right?
Yes.
75 to 85 would be 10. 74 to 85 would be 11. All right, so now we're going to graph this. When we're graphing what's called a residual plot, it always looks like this. And it's basically like this is the straight line, and we're looking to see what it looks like scattered above and below, to see if it really does match a linear model. Okay, so this is our x, which is time, and this is going to be our residual. Now, we have residuals as low as negative 13 and as high as 9. Obviously, we don't have that room to fit that there. So I'm going to make every other 5 so that it fits. And then our x-axis, we have plenty of room to fit everything from 0 to 12, so we don't have to worry about scaling there. Okay, and now we're going to plot the x-coordinate with the residual. So 0, negative 13. 0, negative 13. 2, 0. Go across and create the whole residual plot. 4, 9. 6, 11. 861. Or not 861, 87.
Because
Gentlemen. 10, negative 1. And 12, negative 11. Okay, so what does that look like? Marcus, it looks like a parabola. It looks like a quadratic function. So now the next part of it says, do the residuals show any distinct pattern? So what I mean by that is, does it follow a pattern, or are the points scattered above and below? Is there a pattern or not? Do you guys see a pattern? Everybody? Yes. Okay. So yes, there is a pattern. So because there's a pattern, that's telling us that a linear model is not most representative of this data. Okay? If the data was scattered above and below this line, it would show a better linear model. But because we have something like this, it's no longer a linear model. Okay? Something like a quadratic formula or an exponential formula, which fit this data better, even though we had a really high correlation coefficient. So we could go back to our calculator if we wanted to. Let me just make sure my stat plot is set up right so that I don't mess it up. I changed it earlier today. No, I didn't. Go to Zoom and 9. Does that look like a linear function? No. Right? It looks like something that might be represented by a radical function, or if it was to continue, what would that be? A what? A quadratic. Okay? So a linear model is not the best fit here because there is a pattern in the residual. You understand that? Okay, so let's take a look at another one. That's what I just explained there, so I'm not going to read that to you. It's basically what I just went over. All right, so go back into your edit, clear your L1 and L2, enter the new set of data. Once you've got that, you can pull up your linear regression. Notice that. We'll go over to calc. Choice 4, enter. And this time, you all see a R value or correlation coefficient of 0.88. Okay, so again, what kind of correlation do we find? Nice smile, Kaya.
Strong positive.
Good, it's a strong positive correlation. Is this as strong as the last one though? No, the last one was stronger. But remember, even though that last one was strong, the linear model was not the best because of the pattern in the residual. Okay, so this is strong positive relationship. And now we need our equation. I'm rounding everything to the tenths again. We have y equals 1.3x plus 73.7. Who agrees? Okay, so we're going to go through the same process of calculating the predicted and then calculating the residuals and making a residual plot. Okay, so we have the table set up again. We need to fill in the predicted. How do I do that? Who remembers from before? How do I get the predicted numbers? Go ahead, Ashley. Nice laugh. Good. Get the hour studying into the X, and then find what the model would predict for the GPA. These are the actual GPAs. We're going to find what the model would predict for the GPA. So if you plug in 3, what's 1.3 times 3 plus 73.7, rounded to the nearest whole number? Okay, Marcus? Do it. 1.3 times 3 plus 73.7 to the nearest whole number. Go ahead again.
78, I think.
Who agrees with 78? Okay. Plug in 7, what do we get? Go ahead, Emily. Elizabeth, rather. Who agrees with 83? Okay, keep going all the way across. Okay, I think Kaylee's got them all, so Kaylee's going to read them off to me. You guys just make sure they're correct. What did you get for 2, Kaylee? Keep going. 95. What was 5 again? 80 again. And then 9? Who agrees with Kaylee?
9 and 96.
I got 9.
I got 85.
We got 9 and 85. I think that was correct, actually. You plug in, whoa, just double row. Okay, if you plug in 1.3 times 9 plus 73.7, everybody else agrees it should be 85? We're good? Okay. So now I've got my prediction. How do I calculate my residual? Go ahead, Luke, next line. Good. So predict. You're going to subtract the actual GPA minus the predicted GPA. So it's 78 minus 78, everybody. 0. 80 minus 83. Negative 3. 75 minus 76. Negative 1. 94 minus 88. Hello? 6. 89 minus 84. 89 minus 84? Say it. 5. 92 minus 95. Negative 3. 80 minus 80. 0. 84 minus 85. Negative 1. Okay. So, again, to graph the residual plot, our hour studying is going to remain the x value. The y-axis is going to be our residuals. And in this case, we don't have to do any scaling at all because all of it will fit on the graph. So we're going to start by plotting hour studying 3 and residual 0. Now, be careful with this one because it does not go in order. So you're not going to keep on going to the right of your graph. It does not go in order. Be careful when you're plotting those points. 7, negative 3. 2, negative 1. 11, positive 6. 8, 5. 16, negative 3. 5 and 0. 9 and negative 1. So, in this case, does the residual show a pattern? No. So, is the linear model a good model? Yes. Okay. If there's a pattern, the linear model is not the best choice. If there isn't a pattern and the points are just scattered above and below the residual plot, then it is a good model. So you're going to say no pattern, And then, why does this residual plot show a more appropriate linear model than the one in problem number 1, even though the R value is worse? Because the points are scattered above and below the line without a distinct pattern. Now, I saw Dan do this, so it might even be good to look at it, and I want to show you something. So if I go back into my y equals and put in that equation, 1.3x, except I didn't do 1.3. Second insert point. 1.3x plus 73.7, and I do my stat plot. Looks like a good model, right? If I made this line horizontal, what would it look like? My residual plot, right? So because the points are scattered above and below, my residual plot also shows that they're scattered above and below. It is a good model. And again, your residual plot, look, this horizontal line acts as your line of best fit. Do you see it? You okay, Marcus? Can you go get your lip drink? Okay. So again, this residual plot, the line here that we see here, the original equation, winds up being this line in our residual plot. Okay, it's just turned horizontally. We're good? Okay, so you have 2 exit questions that you're going to try today, and then you can start your homework. You got about 5 minutes to get it done.